a world frozen in time. Close your eyes and imagine stepping outside on a winter morning. The air is crisp and cold against your face. Frost covers every surface, transforming the familiar landscape into something magical and strange. Bare trees stand like sculptures of ice. Your breath forms clouds in the frigid air. This is winter as you know it, a season that comes and goes, a temporary cold that will give way to spring's warmth. Now, imagine that winter never ends. Imagine that the cold deepens year after year, that snow falls and never melts, that ice begins to accumulate in layers that grow thicker with each passing century. Imagine glaciers miles thick spreading across continents, burying entire mountain ranges beneath rivers of frozen water that flow with impossible slowness. Imagine sea levels dropping hundreds of feet as the ocean's water becomes locked in ice, exposing vast areas of land that had been underwater for millions of years. This is not imagination, this is history. For most of the past 2.5 million years, Earth has been locked in an ice age, a period when global temperatures dropped enough to allow massive ice sheets to form and spread across much of the northern hemisphere. And within that ice age, there have been cycles, periods when the ice advanced even further, covering half of North America and most of northern Europe under glaciers thousands of feet thick, and briefer interglacial periods when the ice retreated but never disappeared entirely. The last time glaciers reached their maximum extent was about 20,000 years ago, a period scientists call the last glacial maximum. At that moment in Earth's history, our planet looked dramatically different from the world you know today. The geography was altered, the climate was transformed. Plants and animals that had thrived for millions of years either adapted to the new conditions or went extinct. And humans, our ancestors, lived in this frozen world, hunting mammoth and sheltering in the caves, surviving conditions that would challenge even modern technology. Tonight, we are going on a journey back to that frozen world. We will explore what Earth was like during the Ice Age, how the climate changed, how life adapted, and how these ancient cold periods shaped the planet you live on today. We will discover that the Ice Age is not just ancient history, but a force that carved the landscapes you see, influenced the evolution of countless species including our own, and may not be entirely finished with us yet. Before we begin this journey into Earth's frozen past, I want to ask a small favor. If you're ready to explore the Ice Age with me tonight, to discover what our planet was like when ice ruled the world, tap that like button. It helps this video reach others who might find these calm evening journeys through Earth's history as fascinating as you do. And if you want to make this a regular part of your night, subscribe to the channel. I create videos like this several times a week, each designed to fill your mind with wonder while helping you drift peacefully towards sleep. Now, tell me in the comments, where are you watching from tonight? Are you warm in bed as winter cold presses against your windows? Sitting comfortably while snow falls outside? Or perhaps you're in a place where winter never comes, where the Ice Age's legacy is visible in different ways. I love seeing how this community spans the globe, connecting people across the world that the Ice Age helped shape. Get comfortable now. Adjust your pillow. Let your body sink into the mattress. Let your breathing slow and deepen naturally. Maybe pull your blanket a little closer, feeling grateful for the warmth it provides. Tonight we travel to a time when staying warm required much more than blankets, when survival meant adapting to cold that lasted not for months, but for thousands of years. Our journey begins not 20,000 years ago, but much further back, because to understand the last glacial maximum, we must first understand ice ages themselves, how they form, why they happen, and why Earth has experienced these dramatic cooling periods throughout its long history. Let us start at the very beginning, with the question that must be answered before all others. What exactly is an ice age, and why does Earth experience them at all? Understanding ice ages. On a clear night, if you look up at the stars, you are seeing light that has traveled across vast distances to reach your eyes. Some of those stars are hundreds or thousands of light years away, meaning the light you see was emitted centuries or millennia ago. You are literally seeing into the past, observing the universe as it was when that light began its journey through space. In a similar way, when we study ice ages, we are looking back through time. But instead of observing distant stars, we are reading the records preserved in ice cores, ocean sediments, and ancient rock formations. These records tell a story of dramatic climate changes that have shaped Earth throughout its 4.6 billion year history. An ice age, in the broadest sense, is a long period when Earth's temperature is low enough that permanent ice sheets exist at the poles and often extend far beyond them. By this definition, we are actually living in an ice age right now because Greenland and Antarctica are covered by massive ice sheets. But when most people talk about the ice age, they mean something more specific. The periods within our current ice age when glaciers advanced far beyond the poles, covering huge portions of the continents. To understand this distinction, we need to understand that ice ages work on multiple timescales. There are the long ice ages that last millions of years, periods when Earth's overall climate is cool enough to maintain permanent polar ice. Within these long ice ages, there are shorter cycles that last tens of thousands of years, alternating between glacial periods when ice sheets expand dramatically, and interglacial periods when ice retreats. We are currently living in an interglacial period that began about 11,700 years ago. The ice has retreated from most of the areas it covered 20,000 years ago, but it has not disappeared. Greenland and Antarctica remain frozen, and unless something fundamental changes in Earth's climate system, the ice will likely advance again in the future, though that advance may be delayed or prevented by human-caused climate change. Earth has experienced at least 5 major ice ages over its history, each lasting millions of years. The earliest occurred over 2 billion years ago, during the Precambrian era, when Earth's continents were still forming and the atmosphere was very different from today's. Another major ice age occurred about 700 million years ago during the Cryogenian period, when some evidence suggests Earth may have been almost entirely covered in ice, a snowball Earth scenario that nearly extinguished all life. But the ice age that concerns us tonight, the one that shaped the world you live in, is the most recent one. This ice age, called the Quaternary Glaciation, or sometimes the Pleistocene Ice Age, began approximately 2.6 million years ago, when Earth's climate cooled enough for large ice sheets to form in the northern hemisphere. Why did this cooling happen? The answer involves multiple factors working together over millions of years. One major factor was the formation of the Isthmus of Panama about 3 million years ago. When North and South America connected, ocean currents that had circulated between the Atlantic and Pacific were blocked. This reorganized global ocean circulation patterns and helped cool the climate. Another factor was the positions of the continents. Antarctica had moved to sit over the South Pole, where it accumulated ice. The large landmasses of North America and Eurasia were positioned at high northern latitudes, where ice could form and persist. The arrangement of continents affects how ocean and atmospheric currents flow, which in turn affects climate. But perhaps the most important factors controlling the advance and retreat of ice sheets are subtle changes in Earth's orbit and rotation. These changes, called Milankovitch cycles, after the Serbian scientist who first calculated them, operate on timescales of tens of thousands of years, and are the primary drivers of glacial and interglacial periods. There are 3 main orbital variations. First, the shape of Earth's orbit around the Sun changes over time from more circular to more elliptical and back again. This cycle takes about 100,000 years. When Earth's orbit is more elliptical, seasonal variations in the amount of sunlight reaching Earth are more extreme. Second, the tilt of Earth's axis wobbles between about 22 and 24.5 degrees over a cycle of about 41,000 years. Currently, Earth's axis is tilted at about 23.5 degrees. When the tilt is greater, seasons are more extreme. When the tilt is less, seasons are milder. Third, Earth's axis wobbles like a spinning top, a motion called precession that takes about 26,000 years to complete one cycle. This affects which hemisphere is tilted toward the Sun during its closest approach. These 3 cycles work together to change the amount and distribution of sunlight reaching different parts of Earth's surface. When the cycles align in certain ways, northern hemisphere summers become cooler. This is crucial because ice ages begin not when winters are colder, but when summers are cool enough that winter snow does not completely melt. Snow that survives the summer accumulates year after year, compressing into ice, building into glaciers that begin their slow advance across the landscape. Over the past 800,000 years, these orbital cycles have created a remarkably regular pattern. Glacial periods have occurred about every 100,000 years, each lasting roughly 90,000 years, separated by shorter interglacial periods of 10 to 15,000 years. We are currently about 11,700 years into an interglacial period. Based on past patterns, we might expect the ice to begin advancing again, sometime in the next few thousand years. However, human activities have dramatically increased atmospheric carbon dioxide levels, warming the climate in ways that may delay or prevent the next glaciation for 50,000 to 100,000 years. But 20,000 years ago, during the last glacial maximum, humans had not yet begun to significantly affect global climate. The orbital cycles had aligned to create conditions favorable for ice, and Earth had entered the coldest period of the current ice age. Let us now explore what that world looked like. A world of ice 20,000 years ago, if you could have looked at Earth from space, you would have seen a planet dramatically different from the one you know today. The most obvious change would have been the extent of ice coverage. Massive ice sheets, gleaming white beneath the sun, covered enormous portions of the northern hemisphere continents. The Laurentide ice sheet, the largest of these glaciers, covered almost all of Canada and extended south into what is now the northern United States. At its maximum extent, this single ice sheet stretched from the Atlantic to the Pacific, from the Arctic Ocean to approximately where modern New York, Chicago, and Seattle are located. It contained enough ice that if it melted today, global sea levels would rise by more than 65 feet. The thickness of this ice sheet was staggering. In some places, particularly over what is now Hudson Bay, the ice was more than 2 miles thick. Imagine standing at sea level and looking up at a wall of ice rising 10,000 feet above you, higher than any mountain in the continental United States, except those in Alaska. The weight of this ice was so immense that it actually depressed the Earth's crust beneath it, pushing the land surface down by hundreds of feet. The Cordilleran ice sheet covered much of western Canada and Alaska, while smaller ice caps covered mountain ranges across western North America. In Europe, the Fennoscandian ice sheet covered Scandinavia, parts of Britain, Ireland, and extended across northern Germany and into Russia. The Alps, Pyrenees, and other European mountain ranges had their own extensive glaciers. But the ice sheets were not static, frozen monuments. They were dynamic rivers of ice, flowing outward from their centers under their own immense weight. The ice moved slowly, usually just inches or feet per year in most places, but this slow movement was continuous and relentless. As glaciers advanced, they scraped the bedrock beneath them, carving valleys, smoothing mountains, and carrying rocks and soil hundreds of miles from their origins. At the edges of these ice sheets, where the ice met unfrozen land, the landscape was harsh and barren. Glacial margins were not clean boundaries, but zones of chaos where ice constantly calved and melted, where meltwater streams emerged from under the glacier, carrying sediment that spread across the land, where winds howled across bare ground, scoured by ice. Beyond the ice sheets, but still under their influence, lay vast regions of tundra and permafrost. Tundra is treeless land where the ground remains frozen year-round, just a few feet below the surface, creating a permanently frozen layer called permafrost. During brief summers, the surface might thaw, creating a waterlogged landscape of small lakes and marshes, but the underlying ground remained solid ice. This tundra extended hundreds of miles beyond the glacier's edges, covering much of what is now the northern United States, southern Canada, and a broad band across Europe and Asia. These were cold, windswept lands where only the hardiest plants could survive: grasses, sedges, low shrubs, mosses, and lichens. Yet, despite the harsh conditions, these tundra landscapes supported large populations of animals. South of the tundra, across what is now the American Midwest and much of Europe, lay great grasslands. These were not the warm prairies or meadows you might imagine, but cold steppes where grasses grew during short summers and dried and died during long winters, creating vast expanses of golden grass that fed enormous herds of herbivores. The climate in these regions was not just colder, but fundamentally different from today. Average global temperatures were about 6 degrees Celsius, approximately 11 degrees Fahrenheit, cooler than present. This might not sound like much, but small changes in average temperature have enormous effects on climate. That 6-degree cooling was enough to lock up so much water as ice that sea levels dropped by more than 400 feet. This sea level drop exposed vast areas of continental shelf that are now underwater. A land bridge connected Asia and North America across what is now the Bering Strait, allowing animals and eventually humans to walk between continents. Britain was connected to continental Europe, and you could have walked from France to England across dry land. Indonesia, which today consists of thousands of islands, was part of a large landmass scientists call Sundaland. The climate was not only colder, but also much drier than today. With so much water locked up in ice sheets, less moisture circulated through the atmosphere. Precipitation decreased globally. Many areas that are deserts today, such as the Mojave Desert in North America, actually had more water during the Ice Age than they do now, with lakes filling basins that are dry today. But overall, the world was drier. Wind patterns were also dramatically different. The massive ice sheets created their own weather systems, with cold air sinking over the ice and flowing outward in powerful winds. These winds picked up dust from the barren periglacial regions, creating dust storms that deposited thick layers of fine sediment called loess across many areas. Some loess deposits in China are hundreds of feet thick, representing tens of thousands of years of dust accumulation. The oceans themselves were transformed. With sea level more than 400 feet lower, the shape of ocean basins was different. Coastal currents followed different paths. The mixing of surface and deep waters changed. And most significantly, ocean temperatures dropped. Surface waters in some areas were 10 degrees Celsius, 18 degrees Fahrenheit, cooler than today. This cooling had major effects on ocean life. Cold water can hold more dissolved oxygen than warm water, which benefited some marine organisms. But many species that thrive in warm waters disappeared from high latitudes or went extinct entirely. The great ocean currents that transport heat around the planet shifted their paths and altered their strength. One of the most important of these currents is the Atlantic Meridional Overturning Circulation, sometimes called the Gulf Stream, which carries warm water from the tropics toward the North Atlantic and returns cold water to the south. During the Ice Age, this circulation pattern changed multiple times, sometimes strengthening and sometimes weakening, creating rapid climate shifts that affected temperatures across the northern hemisphere. These shifts happened with surprising speed. Ice core records from Greenland show that temperatures could change by as much as 15 degrees Fahrenheit in just a few decades, sometimes even a few years. These rapid climate fluctuations, called Dansgaard-Oeschger events, occurred repeatedly during the Ice Age. Temperatures would suddenly warm toward interglacial levels, remain relatively stable for a few centuries or millennia, then gradually cool back toward full glacial conditions before the cycle repeated. Scientists are still not entirely certain what caused these rapid oscillations, but they appear to be related to changes in North Atlantic Ocean circulation. When something disrupted the normal circulation pattern, temperatures across the northern hemisphere changed dramatically in response. These rapid climate shifts would have been traumatic for the plants and animals living through them. Ecosystems that had adapted to cold conditions suddenly faced warming temperatures. Species ranges shifted north and south repeatedly. Some organisms could adapt and migrate quickly enough to survive. Others could not and disappeared from the fossil record. Yet through all these changes, through the advancing and retreating ice, through the rapid climate oscillations, life persisted. Animals and plants adapted to conditions that would seem impossibly harsh. And in this frozen world, some of Earth's most magnificent creatures thrived. Life in the frozen world. Picture a landscape of endless grassland stretching to the horizon under a pale sky. The grass is brown and dry, rustling in the cold wind that blows constantly across the plain. In the distance, you see movement. At first, it appears as a dark smudge against the golden grass, but as it approaches, the shapes resolve into individual animals. A herd of large, shaggy creatures with long, curved tusks that sweep up and forward from massive heads. Woolly mammoths, perhaps the most iconic animals of the Ice Age, instantly recognizable from their fossils and from the remarkably preserved specimens found frozen in Siberian permafrost. These magnificent creatures stood up to 13 feet tall at the shoulder and weighed up to 6 tons. Their most striking feature was their coats of long, shaggy hair that hung in curtains from their bodies, providing insulation against the brutal cold. Beneath the long outer hair was a dense undercoat of fine wool that trapped air and created a layer of insulation. The ears were much smaller than those of modern elephants, reducing heat loss. The trunk was relatively short and muscular, and those famous curved tusks, which could grow to 16 feet long, were probably used to sweep snow away from vegetation, to dig up roots and tubers, and in social displays and combat between males. Mammoths were incredibly successful animals, thriving across the northern continents for hundreds of thousands of years. They lived in herds, probably with social structures similar to modern elephants. Females and young traveled together, while adult males lived solitary lives or in small bachelor groups, joining female herds only during breeding season. These animals were not struggling to survive in a hostile environment. They were perfectly adapted to it, as comfortable in the Ice Age tundra as elephants are in African savannas today. They grazed on the grasses and sedges that grew during brief summers and subsisted on dried vegetation and woody shrubs during long winters. Their digestive systems were efficient enough to extract nutrition from this relatively poor quality food. Alongside the mammoths grazed other large herbivores, each adapted to the Ice Age conditions in their own way. Woolly rhinoceroses, smaller than mammoths but still massive animals weighing up to 3 tons, had thick fur coats and 2 horns that they may have used to sweep snow from vegetation. Unlike their modern relatives in Africa and Asia, woolly rhinoceroses had adapted to eating the tough, dry grasses of the Ice Age steppes. Giant ground sloths, some species standing up to 12 feet tall when reared on their hind legs, lived in the Americas. These were not the small, slow-moving tree sloths of today, but enormous animals that walked on their knuckles and could reach high branches to browse on leaves. Their size and thick skin provided protection against the cold, and they had few natural predators due to their sheer bulk. Mastodons, relatives of mammoths but with different body proportions and feeding habits, browsed in the forests and woodlands that existed in more sheltered areas. They had straighter tusks than mammoths and teeth better suited for chewing twigs and leaves rather than grass. Giant beavers, the size of modern black bears, built lodges and dams in the rivers and streams that flowed during summer. Irish elk, despite their name found across Europe and Asia, had the largest antlers of any deer species ever known, spanning up to 12 feet from tip to tip. These impressive structures were grown and shed annually, requiring enormous energy investment, but presumably providing advantages in competition for mates. Herds of horses, smaller than their modern descendants but well adapted to cold climates, ranged across the grasslands of Europe, Asia, and North America. Bison, larger than modern species, grazed in vast numbers. Musk oxen, animals that still survive in the Arctic today, were even more widespread during the Ice Age. These herbivores, collectively known as Megafauna, were hunted by formidable predators. Saber-toothed cats, with their enormous canine teeth that could grow to 11 inches long, ambushed large prey, possibly using their specialized teeth to deliver killing bites to the throat or belly. Cave lions, larger than any lion species alive today, hunted in prides across Europe and North America. Dire wolves, larger and more robust than modern wolves, hunted in packs. Short-faced bears, standing 12 feet tall when upright, were possibly the largest land predators of their time. Some scientists believe they may have been primarily scavengers rather than active hunters, using their long legs to cover vast distances in search of carcasses. Cave bears, also enormous, were probably omnivores that spent much of their time in the caves that give them their name. In the oceans, life also adapted to Ice Age conditions. Whales, seals, and other marine mammals thrived in cold waters rich with nutrients. The lower sea levels meant that ocean upwelling, which brings deep, nutrient-rich water to the surface, occurred in different locations than today, affecting the distribution of marine life. Birds adapted to the Ice Age in various ways. Some species migrated long distances between summer and winter ranges, just as many do today. Others, like the ptarmigan, developed white winter plumage for camouflage in snowy landscapes and grew feathers on their feet for insulation. Scavenging birds like ravens and vultures followed herds of megafauna, feeding on carcasses left by predators or animals that died of disease or harsh weather. The plant life of the Ice Age was equally adapted to cold conditions. In the tundra regions near the ice sheets, vegetation was limited to low-growing species that could complete their life cycles during brief summers. Grasses and sedges dominated, along with mosses, lichens, and small flowering plants that bloomed quickly in spring. The grasslands further south, called Mammoth Steppe, or Tundra Steppe, supported a unique ecosystem that no longer exists today. These were not true tundras because they lacked permafrost in many areas, but they were not typical grasslands either. The plant communities included elements of modern tundra, steppe, and prairie vegetation, creating a mixed ecosystem incredibly productive for large herbivores. In more sheltered regions, particularly at lower latitudes and in river valleys, trees managed to survive. Conifers like spruce, pine, and fir formed open woodlands where conditions allowed. Deciduous trees, including birch, willow, and aspen, grew along watercourses and in protected areas. But true forests were much less extensive than today, restricted to southern regions or areas with favorable microclimates. The plant communities changed dramatically as climate fluctuated through Dansgaard-Oeschger cycles. During warming phases, trees could advance northward, only to retreat again when cooling returned. Plant species that could not migrate quickly enough to track changing conditions went extinct or survived only in small refugia, isolated pockets of suitable habitat where they waited out unfavorable conditions. This migration and isolation created complex patterns of plant distribution that can still be detected today by analyzing the DNA of modern species. Some species that now appear widespread have genetic patterns indicating they survived the Ice Age in just a few refugia, then spread from those areas when conditions improved. Insects and other invertebrates, though less visible in the fossil record than large mammals, were crucial parts of Ice Age ecosystems. Beetles adapted to cold climates left their remains in sediments, and paleontologists can identify these specimens and infer climate conditions based on the species present. Butterflies, moths, and other insects that depend on specific plants, species had to track their host plants as vegetation zones shifted. Freshwater ecosystems were profoundly affected by Ice Age conditions. Lakes formed in basins created by glacial erosion or blocked by glacial deposits. Rivers changed their courses as ice sheets advanced and retreated. Fish populations became isolated in different drainage systems, evolving into distinct species. Amphibians, requiring water for reproduction but unable to tolerate freezing, were restricted to southern regions or areas where thermal springs provided year-round liquid water. The interconnections between all these organisms created complex food webs. Plants captured solar energy and converted it into biomass that herbivores consumed. Predators hunted the herbivores. Scavengers cleaned up the remains. Decomposers broke down organic matter and returned nutrients to the soil. Parasites lived on or in other organisms. The ecosystems were complete and functional, as productive and diverse as ecosystems today, just adapted to much colder conditions. Yet all these adaptations, all this specialized evolution for life in Ice Age conditions, could not protect the megafauna from the wave of extinctions that swept across the world, beginning around 50,000 years ago, and accelerating dramatically about 12,000 years ago. By 11,000 years ago, most of the large animals that had thrived for hundreds of thousands of years were gone. In North America, 34 genera of large mammals went extinct. In South America, 50 genera disappeared. Australia lost its megafauna even earlier, beginning about 46,000 years ago. Europe and Asia also suffered extinctions, though not as severe as on other continents. What caused these extinctions remains one of the great debates in paleontology. The timing coincides both with the end of the last glacial period, when climates were changing rapidly, and with the spread of human populations across the world. Most scientists believe both factors played roles, though the relative importance of each continues to be discussed. Climate change at the end of the Ice Age was dramatic. As temperatures warmed, glaciers melted, sea levels rose, and vegetation zones shifted rapidly. The Mammoth Steppe ecosystem collapsed as changing conditions favored different plant communities. Animals adapted to cold, open landscapes found their habitat shrinking and fragmenting. But humans were also spreading across the continents during this period. Modern humans had evolved in Africa and began migrating out of Africa around 70,000 years ago. By 40,000 years ago, humans had reached Australia. By 15,000 years ago, they had entered the Americas. And everywhere humans arrived, large animals began to disappear. The correlation is striking enough that many scientists believe hunting by humans was at least a contributing factor to megafaunal extinctions. Humans were efficient hunters with advanced weapons and cooperative hunting strategies. Large animals, which had not evolved alongside humans, may have lacked appropriate fear responses. Computer models suggest that even relatively low levels of hunting could drive extinctions when combined with climate stress. Other scientists argue that climate change alone was sufficient to explain the extinctions, pointing out that similar extinction events occurred during earlier climate transitions. They note that many species that went extinct were not obviously favored prey animals, and question whether human populations were large enough to have such dramatic effects. The truth probably involves both factors working together. Climate change stressed ecosystems and pushed some species toward extinction. Human hunting provided an additional pressure that some species could not withstand. The combination proved fatal for much of Earth's megafauna. A few species survived: bison in North America, musk oxen in the Arctic, reindeer and moose across northern Eurasia managed to adapt to the changing conditions and to coexist with humans. But the great diversity of large mammals that had characterized the Ice Age was gone, leaving the world significantly poorer in large animal species. The plants and smaller animals also underwent major changes as glaciers retreated and climates warmed. Forests expanded, covering areas that had been tundra or grassland. Tree species that had survived in southern refugia spread northward, recolonizing landscapes from which they had been absent for tens of thousands of years. The mammoth steppe ecosystem completely disappeared, replaced by boreal forests in some areas, and by modern tundra in others. These ecosystem changes happened with remarkable speed, measured in centuries or even decades in some cases. Within a few thousand years, the landscapes of the Northern Hemisphere were transformed from Ice Age conditions to something recognizable as the modern world. But the Ice Age had left permanent marks on those landscapes, geological and biological legacies that persist to this day. The human story. Among all the species that lived through the Ice Age, one holds special interest for us: our own. Humans not only survived the Ice Age but thrived during it, spreading across the globe, developing complex cultures, and creating the foundations for all human civilization that followed. The story of humans during the Ice Age is not just about survival in harsh conditions. It is about innovation, adaptation, and the development of the cognitive and social abilities that make us uniquely human. The challenges of Ice Age life may have played a crucial role in shaping who we are as a species. Modern humans, Homo sapiens, evolved in Africa approximately 300,000 years ago. For most of that time, we remained in Africa, slowly developing the physical and cognitive traits that distinguish us from earlier human species. But beginning around 70,000 years ago, something changed. Human populations began migrating out of Africa, spreading first into the Middle East, then branching to reach Asia, Europe, and eventually Australia and the Americas. This was not the first time human species had left Africa. Earlier humans, including Homo erectus and Neanderthals, had spread across parts of Asia and Europe. But Homo sapiens was different. Our ancestors did not just survive in these new environments. They adapted, innovated, and ultimately replaced or absorbed all other human species they encountered. When modern humans reached Europe about 45,000 years ago, they entered a world already occupied by Neanderthals, a different human species that had lived in Europe for hundreds of thousands of years and was perfectly adapted to Ice Age conditions. Neanderthals were robust, strong, and had large brains similar in size to ours. They used sophisticated stone tools, controlled fire, cared for their sick and elderly, and may have had symbolic thought and possibly language. Yet, within 15,000 years of modern humans' arrival in Europe, Neanderthals were extinct. The reasons for this extinction are debated, but competition with Homo sapiens was likely a factor. Modern humans had certain advantages: more efficient stone tool technologies, better projectile weapons, more complex social networks, and possibly superior cognitive abilities related to planning, symbolism, and innovation. DNA evidence shows that humans and Neanderthals sometimes interbred, and most people of European and Asian descent carry 1 to 2% Neanderthal DNA today. So Neanderthals did not disappear completely. They were absorbed into the expanding human population. But as a distinct species, they vanished around 40,000 years ago. Living in Ice Age Europe required remarkable adaptations. Humans could not survive on natural physical adaptations alone. We lacked the fur, thick skin, and specialized digestive systems of animals like mammoths or woolly rhinoceroses. Instead, humans survived through culture and technology, using our large brains to find solutions that our bodies could not provide. Clothing was essential. Ice Age humans made sophisticated garments from animal skins, sewing them with bone needles and sinew thread to create fitted clothing that trapped body heat effectively. The evidence for this comes from archaeological sites, where stone scrapers used to prepare hides are found in large numbers, and from sites where bone needles have been preserved. Shelter was equally important. In areas where trees were available, humans likely built wooden structures covered with hides. In treeless regions, they built shelters from mammoth bones covered with hides. Remains of such structures have been found at several sites in what is now Ukraine and Russia, showing circular dwellings with walls made from hundreds of mammoth bones, presumably covered with skins stretched across bone frameworks. Caves provided natural shelter, and many famous Ice Age sites are caves or rock shelters where humans lived for thousands of years. The stratigraphy of these caves, the layers of sediment representing different time periods, contains a detailed record of human occupation, including tools, butchered animal bones, hearths, and occasionally human remains. Fire was crucial for survival. Humans had controlled fire for hundreds of thousands of years before the Ice Age, but during cold periods, maintaining fire became even more critical. Fire provided warmth, light, protection from predators, and the ability to cook food, which made nutrients more accessible and killed parasites. Evidence of fire use is abundant at Ice Age sites. Hearths, areas where fires were repeatedly built, often contain thick deposits of charcoal and ash. Stones were used to contain and reflect heat. Humans developed techniques for starting fires even in cold, damp conditions, using materials like fungus as tinder, and employing friction or sparks from striking stones. Hunting large game was central to Ice Age human survival. The megafauna provided not just meat, but also hides for clothing and shelter, bones and ivory for tools and structures, and sinew for thread. Humans developed increasingly sophisticated hunting technologies during this period. Spear points became more refined, with different styles adapted for different purposes. The Clovis point in North America, the Solutrean points in Europe, and various other tool traditions represent regional innovations. Sometime during the Ice Age, humans invented the atlatl, a spear thrower that used leverage to throw spears with much greater force than possible with arm strength alone. The bow and arrow may have been invented during the late Ice Age, though clear evidence for early bows is rare because wood and cord rarely preserve. But the advantage of bow technology would have been significant, allowing hunters to kill game from greater distances with less risk. Humans also developed sophisticated hunting strategies. They would drive animals toward cliffs or into traps. They would surround herds and isolate individuals. They coordinated their activities, with some hunters driving animals toward others who waited in ambush. These strategies required planning, communication, and social cooperation. Fishing and gathering also contributed to Ice Age human diets. Humans used nets and traps to catch fish, hooks made from bone or antler, and spears with multiple barbed points for spearing salmon and other large fish. They gathered plant foods where available, including nuts, berries, roots, and seeds. During summer months in some regions, plant foods may have provided most of the calories in human diets. Social organization during the Ice Age was probably similar to modern hunter-gatherer societies. People lived in small bands of maybe 20 to 50 individuals, related by blood or marriage. Multiple bands would have formed larger regional groups that came together periodically for trade, ceremonies, and to exchange information and marriage partners. These social networks were crucial for survival. Information about where game was abundant, where plants could be gathered, how to navigate unfamiliar terrain, and what weather patterns to expect would have been shared among groups. Trade networks move valuable materials like high-quality stone for tools, shells for decoration, and other goods across long distances. Language was clearly important during this period. While we cannot know exactly when fully modern language evolved, the complexity of Ice Age human behavior, the evidence for long-distance trade and social networks, and the creation of symbolic art all suggest that humans during this period had language capabilities similar to our own, and what art they created. The Ice Age produced some of humanity's most stunning artistic achievements. Cave paintings in France and Spain, created between 35,000 and 12,000 years ago, depict animals with such skill and vitality that they remain moving to viewers today. The famous caves of Lascaux and Chauvet in France, Altamira in Spain, contain hundreds of images of horses, bison, mammoths, lions, and other animals, painted in ochre, charcoal, and other pigments. These were not crude stick figures, but sophisticated artwork showing understanding of perspective, anatomy, and movement. Some animals are shown in motion, running or turning. Others are depicted with subtle shading that gives them three-dimensional form. The artists who created these works spent hours in dark caves, working by firelight, carefully preparing surfaces and mixing pigments to achieve the effects they desired. The purpose of cave art remains debated. Some scholars believe it was religious or magical, perhaps intended to ensure successful hunting. Others suggest it served social or educational functions, teaching young people about animals or marking territories. It may have been aesthetic expression for its own sake, humans creating beauty in a harsh world. Humans also created portable art during the Ice Age. Small sculptures of animals and humans, carved from ivory, bone, or soft stone, have been found at sites across Europe. The Venus figurines, small female sculptures, often with exaggerated sexual characteristics, may represent fertility symbols, though their exact meaning is unknown. Decorative objects like beads, pendants, and carved bones show that humans valued beauty and symbolism. People wore jewelry made from shells, teeth, and carved ivory. They decorated their tools and weapons with engravings. They created musical instruments, including bone flutes that could play recognizable melodies. All of this artistic production required leisure time when people were not desperately struggling for survival, but had enough security and resources to engage in activities beyond immediate necessity. This suggests that even during the Ice Age, human life was not constant misery, but included periods of relative abundance and social activity. Burial practices provide another window into Ice Age human culture. People buried their dead with care, often including grave goods like tools, weapons, or ornaments. Some burials included red ochre, a pigment that may have had symbolic significance. The fact that people took time to properly bury the dead, investing energy in rituals that had no direct survival value, indicates belief systems and emotional lives similar to our own. Some Ice Age burials are particularly elaborate. At Sungir in Russia, a site about 28,000 years old, archaeologists found burials of adults and children covered with thousands of ivory beads that had been sewn onto their clothing. The time required to create these beads would have been enormous, suggesting these individuals held special status in their communities. The children buried at Sungir, who died young, were buried with elaborate goods they could not have earned through their own accomplishments. This suggests inherited status, meaning Ice Age societies may have had social hierarchies rather than being strictly egalitarian. This is a controversial interpretation, but the evidence from burial practices at least suggests that not all individuals were treated identically in death. Toward the end of the Ice Age, human cultures became increasingly complex and regionally distinctive. Different areas developed characteristic tool styles, artistic traditions, and subsistence strategies. This cultural differentiation suggests growing population sizes and decreasing mobility, as groups became more tied to particular territories. In the Middle East, beginning around 15,000 years ago, some groups began to settle in permanent villages. They still hunted and gathered wild resources, but instead of moving seasonally, they built substantial dwellings and lived in the same location year-round. This marks the beginning of a transition that would eventually lead to agriculture and civilization. The end of the Ice Age, beginning around 19,000 years ago and accelerating after 15,000 years ago, presented both challenges and opportunities for human populations. As climates warmed and ice sheets retreated, sea levels rose, flooding coastal areas where many people likely lived. The rising seas inundated vast areas of continental shelf, destroying archaeological sites and erasing evidence of human occupation. But warming also opened new territories for human habitation. Areas that had been covered by ice or were too cold to support human populations became accessible. Forests expanded, providing new resources. The warming climate made some regions more productive and able to support larger human populations. The extinction of the megafauna removed important food sources but also eliminated dangerous predators. Humans adapted by focusing on smaller game, increasing their reliance on fishing, and in some regions, beginning to domesticate plants and animals. The transition from the Ice Age to the Holocene, our current warm period, set the stage for the agricultural revolution that would transform human society. By 11,000 years ago, when the Ice Age definitively ended and the current interglacial period began, humans had spread to every continent except Antarctica. They had survived the harshest conditions Earth had offered in hundreds of thousands of years. They had adapted, innovated, and thrived, and they were ready to begin the next chapter of human history, building the civilizations that would eventually lead to the world you live in today. The Ice Age shapes the land. The glaciers that covered so much of Earth during the Ice Age were not permanent monuments, but dynamic forces that constantly shaped the landscape beneath them. As ice accumulated and flowed, it carved, scraped, crushed, and moved vast quantities of rock and soil. The landscapes we see today in formerly glaciated regions bear the unmistakable marks of ice sculpting. Imagine standing on a mountain in Switzerland or British Columbia or New Zealand, looking down into a valley that cuts deep into the surrounding peaks. The valley has a distinctive U-shaped cross-section, with steep walls and a relatively flat floor, quite different from the V-shaped valleys carved by rivers. This is a glacial valley, carved by ice that once filled it completely. As glaciers flow down mountain valleys, they scrape and pluck rock from the walls and floor. The immense pressure of thick ice, combined with embedded rocks and boulders that act like sandpaper, grinds away the bedrock. The glacier carries this material down valley, where it may be deposited when the ice melts. At the head of glacial valleys, you often find cirques, bowl-shaped depressions with steep walls, created where glaciers first begin to form. Snow accumulates in these depressions, compacting into ice, which then flows out and down the valley. Multiple cirques at the head of adjacent valleys can create sharp, jagged peaks called horns, the most famous being the Matterhorn in Switzerland. Lakes often fill glacial valleys after the ice retreats. Some of these lakes are quite deep, their basins scoured well below sea level before the ice melted. Fjords, the dramatic steep-walled inlets found in Norway, Chile, New Zealand, and Alaska, are glacial valleys that were carved below sea level and then flooded by rising seas when the ice melted. On a larger scale, the massive continental ice sheets carved the landscape even more dramatically. The Laurentide ice sheet scraped across the Canadian Shield, the ancient rock platform that forms the core of North America, removing soil and weathered rock and exposing bare bedrock. The Great Lakes of North America were carved by lobes of the Laurentide ice sheet that pushed deeply into the landscape, creating basins that filled with meltwater as the ice retreated. Hudson Bay in northern Canada is another legacy of the ice sheets. The enormous weight of ice over this region depressed the Earth's crust by hundreds of feet. When the ice melted about 8,000 years ago, the sea flooded the depressed land, creating the shallow bay. Even now, the land is slowly rebounding upward as it recovers from the weight of the vanished ice, rising about half an inch per year in some areas. The ice transported enormous quantities of rock and sediment. Material scraped from the bedrock became frozen into the base of the glacier, where it acted as an abrasive surface that allowed the ice to grind even more effectively. As glaciers melted, they deposited this material in various formations that geologists used to reconstruct the extent and behavior of ancient ice sheets. Moraines are ridges of rock and sediment deposited by glaciers. Terminal moraines mark the farthest extent of glacial advance, piles of debris left at the glacier's edge. You can often identify these in the landscape as subtle ridges or lines of hills that curve across the terrain. In North America, terminal moraines mark the southern extent of the Laurentide ice sheet, running across the northern United States. Drumlins are streamlined hills formed beneath moving ice sheets, shaped like upside-down spoons with their long axes parallel to ice flow direction. Eskers are long, winding ridges of sand and gravel deposited by streams that flowed through tunnels under the ice. When the ice melted, these stream deposits remained as sinuous ridges crossing the landscape. Glacial erratics are boulders that were transported by ice and left behind when the ice melted, sometimes hundreds of miles from their source. These can be enormous house-sized boulders sitting incongruously on the landscape, composed of rock types that don't match the local geology. These erratic boulders puzzled people for centuries before the theory of ice ages explained their origin. The sediment carried by glaciers, when deposited, created various landscapes. Glacial till, unsorted mixture of clay, sand, gravel, and boulders, covers much of the formerly glaciated regions. In some areas, this till is fertile and supports productive agriculture. In others, particularly where the till is rocky and poorly drained, it creates marginal agricultural land. Loess, wind-blown silt deposited downwind from glacial margins, created thick, fertile deposits across parts of North America, Europe, and especially China. The rich agricultural regions of the American Midwest, including Iowa and Illinois, owe their fertility partly to Loess deposits from the Ice Age. Glaciers also affected landscapes far beyond their margins. Rivers carrying meltwater from the ice sheets were enormously powerful, transporting huge quantities of sediment and carving channels across the landscape. Some of these meltwater channels, now dry or carrying only small streams, are vastly oversized for their current water flow, indicating they once carried far more water. Glacial Lake Missoula in Montana formed when ice dammed a valley, creating a lake containing more water than Lake Erie and Lake Ontario combined. This ice dam failed repeatedly, releasing catastrophic floods that carved the channeled scablands of Washington state, a landscape of deeply eroded channels, towering cliffs, and scattered giant boulders that puzzled geologists until the flooding mechanism was understood in the 1920s. These floods were among the largest known on Earth. Water rushed across eastern Washington at speeds up to 65 miles per hour, carrying icebergs the size of buildings. The floods happened multiple times as the lake reformed and the dam failed repeatedly. The landscape they created is unlike anywhere else on Earth, a testament to the power of glacial meltwater. Sea level changes during the Ice Age also profoundly affected landscapes. When ice sheets locked up water, sea levels dropped by more than 400 feet, exposing vast areas of continental shelf. Rivers extended across these newly exposed lands, cutting valleys that are now submarine canyons on the continental shelf. When the ice melted and sea levels rose again, these river valleys were flooded, creating drowned river valleys called rayas. Chesapeake Bay on the east coast of North America is a raya, the flooded valley of the Susquehanna River. Many coastal inlets and estuaries around the world form this way. The rising seas also created barrier islands, long, narrow islands parallel to coastlines, formed from sand deposited by waves and currents. The Outer Banks of North Carolina, the barrier islands along the Texas coast, and similar features elsewhere all formed as sea levels rose after the Ice Age. Climate changes at the end of the Ice Age affected landscapes even in regions never covered by ice. In the American Southwest, many areas that are desert today were wetter during the Ice Age. Lakes filled basins in Nevada, Utah, and California. Lake Bonneville, the predecessor of the Great Salt Lake, covered much of western Utah and parts of Nevada and Idaho. When this lake drained catastrophically about 14,000 years ago, it cut deep canyons and left beaches on mountains far above the current water level. In North Africa, the Sahara Desert was much wetter during some periods, with rivers flowing and lakes dotting the landscape. Rock art from these periods shows humans hunting animals like elephants, giraffes, and crocodiles in regions that are now barren desert. These green Sahara periods occurred during specific orbital configurations that increased summer rainfall in the region. Australia, which was not glaciated during the Ice Age, nevertheless experienced major climate changes. the continent became much drier, and many large lakes present during wetter periods dried up or shrank dramatically. These climate changes, combined with the arrival of humans about 50,000 years ago, contributed to the extinction of Australia's megafauna. The Ice Age landscapes of the southern hemisphere differed from the north in important ways. With less land area at high southern latitudes and with Antarctica already covered by ice, the southern ice sheets were less extensive than those in the north. But glaciers did expand in the Andes, New Zealand, and on islands in the Southern Ocean. New Zealand's South Island had an ice cap that flowed down valleys and reached the sea in many places. The fjords of the southwestern coast, such as Milford Sound, were carved by these glaciers. When the ice retreated, the valleys flooded, creating the dramatic landscapes that attract visitors today. The glacial history of mountains worldwide created landscapes that remain spectacular today. The Alps, Himalayas, Rockies, Andes, and other ranges all show clear evidence of Ice Age glaciation. Many of these mountains still have glaciers, though most are shrinking rapidly due to the current climate warming. The ice sheet's weight had another lasting effect. It depressed the Earth's crust beneath them. When ice miles thick sits on the land for thousands of years, the underlying crust sinks into the mantle beneath. This process is called isostatic depression. When the ice melts, the crust slowly rebounds upward, a process called post-glacial rebound or isostatic rebound. This rebound continues today in formerly glaciated regions. Scandinavia and Canada are slowly rising, in some places by about half an inch per year. This has practical effects. Coastlines are emerging from the sea, harbors are becoming shallower, and maps must be periodically updated to reflect the changing relationship between land and sea. The rebound is not uniform. Areas that were beneath the thickest ice rise fastest, while regions away from the ice sheets, which were actually pushed upward by the displaced mantle material, are slowly sinking. This creates complex patterns of relative sea level change, with some areas experiencing falling sea levels due to land rising faster than the ocean, while other areas see rising sea levels. The effects of Ice Age climate on permafrost extended far beyond the ice sheets themselves. Permafrost, permanently frozen ground, formed across much of the northern hemisphere. In some areas, ice wedges formed as repeated annual freezing and thawing created polygon-shaped patterns visible from the air. These ice wedges could grow to enormous sizes, containing more ice than the surrounding soil. When permafrost thaws, as it is doing in many Arctic regions today due to climate warming, it can cause dramatic landscape changes. The ground subsides as ice melts, creating thermokarst, a landscape of irregular depressions and lakes. Infrastructure built on permafrost can collapse. And as frozen organic matter thaws and decomposes, it releases carbon dioxide and methane, greenhouse gases that contribute to further warming. The Ice Age also affected landscapes through its impact on vegetation. Without tree cover, soil erosion increased in many areas. Wind carried dust across continents, creating thick loess deposits. Rivers, without vegetation to stabilize their banks, wandered across broad floodplains, constantly shifting their courses. When forests returned at the end of the Ice Age, they stabilized the landscape, roots held soil in place. Leaf litter created organic matter that improved soil structure. Trees modified local climate, creating cooler, moister conditions that supported different plant and animal communities. The legacy of Ice Age landscape changes remains visible across much of the northern hemisphere. The rolling hills of the American Midwest, the lakes of Minnesota and Wisconsin, the rocky terrain of the Canadian Shield, the fjords of Norway, the lochs of Scotland, the distinctive mountains of the Alps, all bear the marks of ice. Understanding these landforms requires understanding the Ice Age forces that created them. The Ice Age Earth's climate system. To truly understand what Earth was like during the Ice Age, we must understand not just the ice sheets and the cold temperatures, but the entire climate system and how it operated during glacial periods. The climate system is complex, involving interactions between the atmosphere, oceans, ice, land surface, and living organisms. During the Ice Age, all these components behaved differently than they do today. The atmosphere during the last glacial maximum contained significantly less carbon dioxide than today's atmosphere. Ice cores from Antarctica provide a detailed record of past atmospheric composition, with air bubbles trapped in the ice preserving samples of ancient atmosphere. These cores show that carbon dioxide levels during the glacial maximum were about 190 parts per million, compared to about 280 parts per million during warm interglacial periods and over 400 parts per million today. This lower carbon dioxide level was both a cause and an effect of cold temperatures. Lower CO2 meant less greenhouse warming, contributing to the cold climate. But the cold climate also caused CO2 levels to drop through processes we're still working to fully understand. The oceans hold much more carbon dioxide when water is cold, so glacial oceans absorb CO2 from the atmosphere. Changes in ocean circulation also affected how much CO2 was stored in deep waters versus released to the atmosphere. Methane levels were also lower during glacial periods, about half the interglacial levels. Methane is a more powerful greenhouse gas than CO2, though it's present in much smaller quantities. The lower methane levels during glacials reflected reduced emissions from wetlands, which shrank as climates became colder and drier. The lower greenhouse gas levels meant that Earth's atmosphere retained less heat. More of the sun's energy that reached Earth was radiated back to space instead of being trapped near the surface. This created a feedback loop. Lower temperatures led to lower greenhouse gases, which led to even lower temperatures. Atmospheric circulation patterns were dramatically different during glacial periods. The massive ice sheets created their own weather systems. Cold, dense air sank over the ice and flowed outward in strong winds. The boundary between cold air masses over the ice sheets and warmer air to the south was sharper than modern boundaries, creating powerful storm systems. The jet streams, fast-moving air currents in the upper atmosphere, shifted their positions. During glacial periods, the polar jet stream moved southward, bringing cold Arctic air to lower latitudes. The subtropical jet stream also shifted, affecting rainfall patterns in regions like the Mediterranean and the Middle East. These circulation changes affected weather patterns globally. Some regions became drier, others wetter. The monsoons that bring critical rainfall to parts of Asia and Africa weakened or shifted their timing. Trade winds that normally blow from east to west across the tropics may have been weaker, affecting ocean currents and tropical climates. The ocean's role in the Ice Age climate system was crucial. Oceans cover 70% of Earth's surface and store enormous amounts of heat. They transport heat from equator to poles through currents, moderating temperatures and making Earth more habitable. During the Ice Age, ocean circulation patterns changed in ways that amplified the cooling. One of the most important ocean circulation patterns is the Atlantic meridional overturning circulation. In this system, warm surface water flows from the tropical Atlantic toward the north, releasing heat to the atmosphere along the way. As this water cools and becomes saltier through evaporation, it becomes denser and sinks in the North Atlantic. This deep water flows southward, eventually reaching the Southern Ocean and the Pacific, where it slowly rises back to the surface over hundreds of years. During the Ice Age, this circulation changed multiple times. When large amounts of fresh water from melting ice sheets entered the North Atlantic, it reduced the water's salinity and density, preventing it from sinking. This weakened or shut down the circulation, causing rapid cooling in the North Atlantic region and affecting climate worldwide. These shutdown events may explain the rapid climate oscillations seen in ice core records. Sea ice coverage was much more extensive during glacial periods. In winter, sea ice extended far south in the North Atlantic, reaching as far as Spain. In the Southern Ocean, sea ice extended farther north from Antarctica. This ice reflected more sunlight back to space, contributing to cooling. It also acted as a barrier between ocean and atmosphere, reducing the exchange of heat and gases. The increased sea ice had major effects on marine ecosystems. It limited the area where plankton could photosynthesize, reducing the ocean's primary productivity in high latitudes. But it also created habitat for animals adapted to ice, including seals and penguins. Ocean temperatures were lower throughout the water column, not just at the surface. Deep ocean temperatures, which today are around 2 to 3 degrees Celsius, were even colder during glacials. This cold, dense water could hold more dissolved oxygen than warmer water, potentially benefiting deep-sea organisms. The lower sea level exposed continental shelves, changing the shape of ocean basins and affecting currents. Shallow seas that had provided mixing between different water masses disappeared. The Mediterranean Sea became nearly isolated from the Atlantic during periods of very low sea level, and its salinity increased dramatically. The ice sheets themselves were dynamic parts of the climate system. Ice reflects about 80 to 90% of incoming solar radiation back to space, much more than rock, soil, or vegetation, which absorb most sunlight. This meant that as ice sheets grew, they increased Earth's albedo, its overall reflectivity, causing more cooling and a positive feedback loop. But ice sheets were not stable. They flowed under their own weight, advancing and retreating based on the balance between snow accumulation and melting. Internal dynamics of the ice, including the flow of water at the base of glaciers, could cause sudden collapses or surges where large portions of ice sheets moved rapidly. Ice shelves, floating extensions of ice sheets that covered parts of the ocean around Antarctica and possibly around northern ice sheets, could become unstable and break up. When ice shelves collapse, the ice sheets behind them can flow faster toward the ocean, rapidly raising sea levels. This happened repeatedly during transitions from glacial to interglacial periods. The land surface also participated in climate feedbacks. When ice covered the land, the underlying soil and rock had very different properties than vegetation-covered land. Ice-covered land absorbed less solar energy, contributing to cooling. But as ice retreated and vegetation returned, the land surface darkened and absorbed more energy, contributing to warming. Vegetation changes during the Ice Age affected climate through multiple mechanisms. The forests that covered much of the northern hemisphere during warm periods were replaced by grasslands, tundra, or bare ground during glacials. This changed how much sunlight was reflected, how much moisture was released to the atmosphere through plant transpiration, and how much carbon was stored in plants and soils. The carbon stored in vegetation and soils is substantial. When forests are replaced by grasslands or tundra, less carbon is stored in living plants, and more is stored in soils. But cold conditions slow decomposition, allowing organic matter to accumulate. Peatlands, wetlands where dead plant material accumulates because cold. Waterlogged conditions prevent complete decomposition, stored large amounts of carbon during glacial periods. Dust in the atmosphere increased dramatically during glacial periods. With less vegetation to hold soil in place, strong winds could lift dust from deserts and from the bare ground around ice sheets. This dust traveled thousands of miles, eventually settling on ice sheets, in oceans, and on land surfaces far from its source. The effects of dust were complex. Dust landing on ice sheets darkened them slightly, making them absorb more sunlight and potentially accelerating melting. Dust falling in oceans fertilized plankton growth by providing iron and other nutrients. Increased plankton growth absorbed CO2 from the atmosphere, contributing to the low glacial CO2 levels. The dust also affected the radiative balance of the atmosphere. Dust particles can both reflect sunlight back to space and absorb infrared radiation emitted by Earth's surface. So, their overall effect on temperature depends on their properties and altitude. The net effect was probably cooling, but the magnitude remains uncertain. All these components of the climate system, atmosphere, oceans, ice, land surface, and vegetation, interacted in complex ways. Changes in one component affected others, creating feedback loops that could amplify or dampen initial changes. Understanding these feedbacks is crucial for predicting how climate will respond to current human-caused warming. The study of Ice Age climate helps us understand these feedbacks. By examining how the climate system behaved under conditions very different from today, we can test our understanding of climate dynamics and improve climate models. The Ice Age provides a natural experiment, showing how Earth's climate responds to changes in solar energy distribution, greenhouse gas levels, and ice sheet extent. One of the most important lessons from Ice Age climate research is that the climate system can change rapidly. For most of human history, people assumed climate change slowly, taking thousands of years for significant shifts to occur. But ice core records show that during the Ice Age, temperature could change by 10 to 15 degrees Fahrenheit in just a few decades. These rapid changes must have been traumatic for ecosystems and for human populations. Imagine living through a shift where summer temperatures dropped by 10 degrees in 20 years, where rainfall patterns completely changed, where the plants and animals your community depended on disappeared or moved to different regions. Yet life survived these changes, adapting or migrating to more suitable areas. The mechanisms behind rapid climate changes are still being investigated, but they clearly involve the ocean circulation changes mentioned earlier. When the Atlantic overturning circulation weakened or shut down, it caused rapid cooling in the North Atlantic region within years to decades. When circulation resumed, warming was equally rapid. These abrupt changes happened repeatedly during the Ice Age, creating a climate that oscillated between cold and less cold conditions. During the depths of glacial periods, Earth was in what scientists call stadial conditions, very cold with extensive ice. These stadials were interrupted by warmer interstadial periods lasting hundreds to thousands of years, when temperatures rose closer to interglacial levels before cooling resumed. This pattern of rapid oscillations is very different from the relatively stable climate of the past 10,000 years. During the current interglacial period, temperatures have fluctuated, but without the dramatic swings seen during glacial times. This stability may have been crucial for the development of agriculture and civilization, allowing humans to establish permanent settlements and rely on predictable seasonal patterns. The transition from glacial to interglacial conditions, which occurred most recently between 19,000 and 11,000 years ago, was not smooth or gradual. Temperatures rose rapidly around 14,000 years ago, then suddenly cooled again during the Younger Dryas period from about 12,000 years ago, 800 to 11,700 years ago, before warming resumed and ushered in the stable Holocene climate. The Younger Dryas cooling, which lasted about 1,000 years, may have been triggered by a massive influx of fresh water into the North Atlantic from glacial Lake Agassiz, a huge lake formed by melting ice in North America. This fresh water disrupted ocean circulation, causing rapid cooling. When circulation resumed, temperatures rose quickly. This episode demonstrates how sensitive the climate system is to sudden changes. A large influx of fresh water, caused by natural ice sheet melting, triggered cooling that affected the entire northern hemisphere. Today, as Greenland's ice sheet melts due to human-caused warming, scientists worry about similar disruptions to ocean circulation, though the timescales and mechanisms differ from the Younger Dryas. The end of the Ice Age, the transition to the warm, stable Holocene, transformed Earth's climate system. Ice sheets melted, releasing enormous volumes of fresh water to the oceans. Sea levels rose over 400 feet. Coastal areas were flooded. Ocean circulation patterns reorganized. Atmospheric circulation shifted. Vegetation zones moved poleward. These changes created the world you live in today, a world shaped by Ice Age climate and its ending. The climate system you experience, with its current patterns of winds, currents, precipitation, and temperature, is partly a legacy of how the Ice Age climate system collapsed and reorganized into a new configuration. Understanding Ice Age climate is not just about understanding the past. It helps us comprehend how climate works, how different components interact, and how sensitive the system is to changes. This knowledge is crucial, as humans are now changing the climate system faster than any natural change in the past 10,000 years, creating conditions Earth has not experienced since before the Ice Age began. The Ice Age's living legacy. The Ice Age ended 11,700 years ago, but its effects persist today in countless ways. The landscapes we see, the species we share the planet with, even our own human biology and culture, all bear marks of the Ice Age. Understanding this legacy helps us see how deeply the Ice Age shaped the modern world. Begin with the landscapes. Every formerly glaciated region bears unmistakable signs of ice. The Great Lakes of North America, the deepest and largest group of freshwater lakes on Earth, are glacial creations. The thousands of lakes in Minnesota, Wisconsin, and Canada formed in depressions left by melting ice blocks. The fertile farmlands of the Midwest rest on sediments deposited by glaciers and their meltwater. The fjords of Norway, Alaska, Chile, and New Zealand are glacial valleys flooded by rising seas. Yosemite Valley in California, carved by glaciers flowing from the Sierra Nevada, displays classic glacial features, including hanging valleys, where tributary glaciers once joined the main valley. The cirques, U-shaped valleys, and sharp peaks that define mountain ranges worldwide are Ice Age creations. Even in regions far from ice sheets, the Ice Age left its mark. The pluvial lakes of the American West, formed during wetter glacial periods, left behind salt flats, ancient shorelines, and isolated fish species that evolved in no-dry basins. The lowest deposits that created rich agricultural soils in China, the American Midwest, and parts of Europe were blown from glacial margins. The biological legacy is equally profound. Many species alive today evolved during the Ice Age or were shaped by its pressures. Their distributions, genetic diversity, and even their physical characteristics often reflect Ice Age climate changes. Consider the reindeer or caribou, animals perfectly adapted to cold climates with thick fur, wide hooves for walking on snow, and the ability to dig through snow to reach vegetation. These adaptations evolved during the Ice Age. Reindeer thrived during glacial periods, spreading across the northern hemisphere. As climates warmed, their range contracted, and today they live only in Arctic and subarctic regions. Musk oxen, another Ice Age survivor, show similar patterns. These animals, with their thick coats and ability to withstand extreme cold, were widespread during glacials but are now restricted to the Arctic. Their populations went through genetic bottlenecks as their habitat shrunk, and today's musk oxen have relatively low genetic diversity, all descended from a small number of individuals that survived the transition to warm climates. Arctic foxes, ptarmigan, and many other species show this same pattern, widespread during the Ice Age, restricted to high latitudes or high altitudes today. These are relic populations, survivors in places where Ice Age conditions persist. Other species show different patterns. Brown bears, which evolved during the Ice Age, adapted to both cold and warm environments and remain widespread across the northern hemisphere. Wolves similarly adapted to various climates and habitats. These species' flexibility allowed them to survive climate changes that eliminated more specialized animals. Plant species also bear Ice Age legacies. Many trees now common in Europe survived the Ice Age in refugia in southern Europe, the Balkans, and the Iberian Peninsula. As climates warmed, they spread northward, recolonizing landscapes from which they had been absent for 100,000 years. The genetic patterns of these trees reveal their history. European beech trees, for example, show genetic patterns indicating they survived the Ice Age in just a few refugia, then spread from those areas to cover much of Europe. The DNA of modern trees allows scientists to map these ancient refugia and trace the paths trees took as they migrated northward. Some species did not survive the Ice Age's end. The extinction of most megafauna between 50,000 and 10,000 years ago removed species that had evolved over millions of years. Mammoths, mastodons, saber-toothed cats, giant ground sloths, and many others disappeared, leaving ecosystems fundamentally different from their Ice Age configurations. The extinction of these large animals had cascading effects. Mammoths, for instance, helped maintain the mammoth steppe ecosystem by knocking down trees, fertilizing the soil with their dung, and compacting snow in winter, making it easier for other animals to move around. When mammoths disappeared, the ecosystem changed, trees spread. The grasslands that supported diverse animal communities transformed into forests or tundra with fewer large animals. In North America, the extinction of most large predators left an ecosystem with abundant elk, deer, and other herbivores, but few animals to control their numbers. Native Americans filled part of this role, hunting these animals and using fire to manage landscapes. When European diseases killed most Native Americans in the 16th and 17th centuries, herbivore populations exploded, affecting vegetation patterns. The Ice Age also left a legacy in the ocean. Many marine species evolved during glacial periods or show genetic patterns reflecting how glaciers affected ocean basins. Fish populations that were once connected became isolated in different refugia when sea levels dropped, and later reconnected when seas rose, creating complex patterns of genetic diversity. Coral reefs, which are very sensitive to sea level changes, were deeply affected by glacial cycles. During glacials, when sea levels dropped, reefs that had grown near the surface were left high and dry, killing the corals. New reefs had to form at lower elevations. When seas rose during interglacials, these reefs could grow upward, tracking the rising water. The Great Barrier Reef off Australia experienced these cycles repeatedly. The current reef is quite young, having formed mostly since sea levels stabilized about 6,000 years ago. But beneath it lie the remains of earlier reefs that grew during previous interglacial periods, separated by periods when the continental shelf was dry land. Humans themselves are products of the Ice Age. Our species evolved in Africa, but our expansion across the world, our development of complex tools and clothing, and our adaptations to diverse environments all occurred during the Ice Age. The cognitive abilities that distinguish modern humans from earlier species may have been shaped by Ice Age pressures. The genetic diversity of human populations reflects Ice Age climate changes. When populations were isolated from each other by ice sheets, deserts, or oceans, they evolved different genetic characteristics. When they came back into contact as climates changed, they sometimes interbred, sometimes competed. The complex patterns of human genetic variation we see today are partly a product of these Ice Age population movements and isolations. Human cultures also bear Ice Age marks. Many indigenous traditions include memories that may date back to the Ice Age. Stories of great floods might remember the rapid sea level rise at the Ice Age's end. Tales of giant animals might preserve memories of megafauna. The knowledge of how to survive in harsh climates, maintained by Arctic peoples, represents continuous cultural transmission across thousands of years. Even human behavior and psychology may have been shaped by Ice Age conditions. Living in small groups, cooperating to hunt large game, sharing resources during lean times, planning for seasonal changes, these behaviors that were crucial for Ice Age survival may have become deeply ingrained in human psychology. Some evolutionary psychologists argue that many modern human behaviors and preferences reflect adaptations to Ice Age conditions. Though these arguments remain controversial, the Ice Age also left a legacy in Earth's carbon cycle. The carbon stored in soils, peatlands, and permafrost represents thousands of years of accumulation. As permafrost thaws due to current climate warming, this ancient carbon is being released to the atmosphere as carbon dioxide and methane, contributing to further warming. Estimates suggest that permafrost contains about twice as much carbon as the entire atmosphere currently holds. Not all of this will be released. Some permafrost will remain frozen even under significant warming, but the potential for major carbon releases exists. This represents a feedback where past Ice Age conditions affect current climate through the legacy of frozen organic matter. The Ice Age's legacy even extends to human diseases. Some pathogens that affect humans today evolved during the Ice Age, adapting to the animals that humans hunted or domesticated. When humans transitioned from hunting to farming after the Ice Age ended, they came into closer contact with domesticated animals, allowing diseases to jump from animals to humans. The influenza viruses, for instance, probably originated in waterfowl, but adapted to pigs and then to humans. This process was facilitated by the domestication of pigs after the Ice Age. Similarly, many other diseases that plague humans, from smallpox to tuberculosis to measles, likely emerged during the transition from the Ice Age hunter-gatherer lifestyle to settled agricultural communities. Archaeological sites from the end of the Ice Age provide crucial evidence for understanding this period. Göbekli Tepe in Turkey, built about 11,500 years ago, just as the Ice Age was ending, shows remarkably sophisticated architecture for a society that had not yet developed agriculture. This suggests that the end of the Ice Age allowed social complexity to develop even before farming began. The site consists of massive stone pillars arranged in circles, carved with images of animals including snakes, scorpions, foxes, and lions. Creating these structures required organizing many people to quarry, transport, and erect stones weighing many tons. This level of social organization was previously thought to require agriculture, but Göbekli Tepe demonstrates that complex societies could develop among hunter-gatherers in the favorable conditions at the Ice Age's end. As the Ice Age ended and climates stabilized in the Holocene, human societies underwent rapid changes. In the Middle East, the Fertile Crescent saw the independent development of agriculture between 11,000 and 10,000 years ago. Similar developments occurred independently in China, Mesoamerica, the Andes, and other regions. The stable climate of the Holocene allowed predictable seasonal patterns that made agriculture possible. Would humans have developed agriculture if the Ice Age had continued? Probably not. The rapid climate fluctuations characteristic of glacial periods would have made agriculture too risky. Crops need predictable seasons to grow. The stability of the past 11,000 years provided the conditions necessary for farming to develop and spread. Agriculture transformed human society, allowing larger populations, permanent settlements, and eventually the rise of cities and civilizations. In this sense, all of human civilization is a legacy of the Ice Age's end, built on the stable climate platform that the transition to the Holocene provided. But the Ice Age may not be entirely finished with us. We are living in an interglacial period that has already lasted longer than some previous interglacials. Based on orbital cycles, we might expect glaciers to begin advancing again within the next few thousand years. However, human greenhouse gas emissions have altered the climate so dramatically that the next glaciation will likely be delayed by tens of thousands of years or more. This raises profound questions. Are we preventing the next Ice Age? Are we ending the natural cycle of glacial and interglacial periods that has characterized Earth's climate for the past 2.5 million years? The answer appears to be yes, at least temporarily. The amount of carbon dioxide we have added to the atmosphere will take thousands of years to be removed by natural processes, keeping the climate warm enough to prevent glaciation even if orbital cycles favor ice sheet growth. In effect, humans have become a geological force capable of altering climate on timescales previously controlled only by orbital mechanics and natural carbon cycle processes. This is why some scientists have proposed naming our current time the Anthropocene, a new geological epoch defined by human impacts on Earth's systems. The legacy of the Ice Age thus includes not just the landscapes and species it left behind, but also the stable climate platform it created when it ended. A platform that allowed human civilization to flourish, but that we are now fundamentally altering. Understanding this legacy helps us appreciate both how much Earth's climate has changed in the past and how dramatically we are changing it now. How scientists discovered the Ice Age. For most of human history, people did not realize that Earth had experienced ice ages. The evidence was all around them. The strange boulders sitting in the wrong places, the U-shaped valleys cutting through mountains, the gravel and clay covering hillsides. But no one understood what had created these features. Various explanations were proposed. Some thought the boulders had been transported by Noah's flood, as described in the Bible. Others suggested that boulders had been carried by icebergs floating on a global ocean. The true explanation, that massive ice sheets had covered much of the northern hemisphere, seemed too fantastic to believe. The first person to seriously propose an ice age was a Swiss scientist named Louis Agassiz. In the 1830s, Agassiz was studying glaciers in the Alps and became convinced that they had once been much more extensive. He noticed that alpine valleys far below current glacier positions showed the same types of scratches, polish, and debris deposits found near active glaciers. In 1837, Agassiz presented his Ice Age theory to the Swiss Society of Natural Sciences. The reception was hostile. Most scientists found the idea absurd. They believed Earth had been steadily cooling since its formation as a molten ball, not that it had undergone cycles of extreme cold, separated by warmer periods. But Agassiz persisted. He traveled to other regions, documenting evidence of former glaciation. In Scotland, he found the same glacial features. In North America, where he eventually settled and taught at Harvard University, he found even more extensive evidence. Gradually, other scientists began to accept his ideas. By the 1860s, the reality of past ice ages was widely accepted in the scientific community. But many questions remained. How many ice ages had there been? What caused them? When did they occur? Scientists spent the next century and a half developing answers to these questions. Early estimates of ice age timing were based on geological evidence. Scientists tried to calculate how long it would take for certain processes to occur, like the weathering of rocks or the deposition of sediments. These estimates were crude and often wrong by large margins, but they established that ice ages occurred deep in the past, long before recorded human history. The The discovery of radioactivity in the 1890s provided new tools for dating rocks and sediments. Radiocarbon dating, developed in the 1940s, could date organic materials up to about 50,000 years old. This allowed scientists to date the most recent glaciation with much greater accuracy. Other radiometric dating techniques allowed scientists to date much older materials. By measuring the decay of uranium to lead or potassium to argon, scientists could date rocks millions or even billions of years old. These techniques revealed that ice ages had occurred repeatedly throughout Earth's history, not just recently. The most detailed information about ice ages comes from ice cores drilled from Antarctica and Greenland. These cores, cylinders of ice extracted by drilling straight down through ice sheets, contain layers representing annual snowfall going back hundreds of thousands of years. By analyzing the ice and the air bubbles trapped within it, scientists can reconstruct past temperatures, atmospheric composition, precipitation patterns, and even dust levels. The ice cores from Antarctica extend back about 800,000 years, covering the past 8 glacial interglacial cycles. These cores show with remarkable clarity the regular pattern of glacial and interglacial periods, the rapid climate oscillations during glacials, and the relatively stable conditions during interglacials. They provided the definitive proof that Earth's climate has undergone dramatic changes repeatedly in the recent past. Ocean sediment cores provide an even longer record. These cores, drilled from the ocean floor, contain sediments deposited continuously over millions of years. By analyzing the types of organisms preserved in these sediments and the chemical composition of their shells, scientists can reconstruct ocean temperatures and ice volume going back tens of millions of years. One crucial technique involves analyzing oxygen isotopes in the shells of tiny marine organisms called foraminifera. When ice sheets grow, they preferentially lock up water containing the lighter oxygen-16 isotope, leaving the ocean relatively enriched in the heavier oxygen-18 isotope. Organisms that build their shells from ocean water incorporate these isotopes in proportions that reflect the ocean's composition. By measuring oxygen isotope ratios in forams shells from different sediment layers, scientists can determine how much ice existed on land at different times in the past. This technique has revealed the detailed history of glacial cycles over the past several million years. In the 1920s, a Serbian scientist named Milutin Milankovic calculated how changes in Earth's orbit affect the distribution of sunlight reaching Earth's surface. He showed that these orbital variations created cyclical changes in solar energy input that matched the timing of glacial cycles. Milankovic's theory was controversial for decades. Some evidence seemed to support it, but other evidence didn't fit. The problem was that the geological evidence was not precise enough to definitively test the theory. It wasn't until ocean sediment cores provided accurate timing of glacial cycles that Milankovic's theory could be properly tested. In the 1970s, studies of ocean cores showed that glacial cycles did indeed match the timing predicted by orbital variations, specifically the 100,000-year cycle of orbital eccentricity. This confirmed that orbital forcing was the primary driver of ice age cycles, vindicating Milankovic's work done 50 years earlier. But scientists also realized that orbital forcing alone couldn't explain the magnitude of climate changes. The changes in solar energy reaching Earth due to orbital variations are relatively small. Something must amplify these small changes into the dramatic climate shifts recorded in ice cores and ocean sediments. This led to the recognition of feedback mechanisms in the climate system. Lower temperatures lead to more ice, which reflects more sunlight, causing more cooling. Lower temperatures also reduce greenhouse gas levels, causing additional cooling. These feedbacks amplify the initial orbital forcing, creating the large climate changes we observe. Understanding these feedbacks required studying all components of the climate system: atmosphere, oceans, ice sheets, land surface, and biosphere. Scientists developed computer models that simulate these components and their interactions. By running these models under different conditions, they can test hypotheses about how the climate system works. Modern climate models can reproduce the major features of ice age climates when given appropriate inputs like orbital parameters, greenhouse gas levels, and ice sheet extent. This gives scientists confidence that they understand the basic mechanisms driving Ice Age cycles, though many details remain uncertain. One area of active research involves understanding the rapid climate changes during glacials, the Dansgaard-Oeschger events. These seem to involve changes in ocean circulation, but the exact mechanisms and triggers remain debated. Some scientists think changes in ice sheet behavior triggered ocean circulation changes. Others think atmospheric changes or even solar variability might have played roles. Another puzzle involves the 100,000-year cycle. While this matches the orbital eccentricity cycle, some scientists think eccentricity itself is too weak to drive glacial cycles, and that the 100,000-year pattern actually reflects internal dynamics of ice sheets interacting with orbital precession and tilt cycles. The debate continues. The study of ice ages has also revealed how sensitive Earth's climate is to changes in greenhouse gases. The relatively small decrease in CO2 from 280 parts per million to 190 parts per million contributed to cooling of about 6 degrees Celsius. This suggests that the much larger increase in CO2 we're causing today, from 280 to over 400 parts per million, will have substantial warming effects. Indeed, the study of past climates provides crucial context for understanding current climate change. It shows that Earth's climate can change dramatically. It reveals the feedback mechanisms that amplify initial changes. It demonstrates that rapid changes are possible when certain thresholds are crossed. And it shows the profound effects climate changes have on ecosystems and species. The story of how scientists discovered and came to understand ice ages is itself remarkable. It required evidence from multiple disciplines: geology, paleontology, chemistry, physics, and biology. It required developing new technologies from ice core drilling to isotope analysis to computer modeling, and it required scientists to think on timescales far beyond human experience, to understand processes that take thousands or millions of years to unfold. Today, Ice Age research continues. Scientists are drilling deeper ice cores, hoping to extend the Antarctic record past 800,000 years to 1.5 million years. They're developing more sophisticated climate models. They're studying how ice sheets behave, information crucial for predicting future sea level rise. They're investigating the causes of rapid climate changes, which could be relevant to understanding how fast climate might change in the future. The ice ages, once unknown and then thought to be simple periods of cold, have been revealed as complex dynamic times when Earth's climate system underwent dramatic reorganizations. Understanding them has revolutionized our knowledge of how climate works and how profoundly it shapes the world we inhabit. The future ice age that may never come. Based on orbital cycles, scientists can predict when conditions should be favorable for the next glaciation to begin. The calculations suggest that declining summer solar energy in the northern hemisphere should reach thresholds that trigger ice sheet growth sometime in the next few thousand years, perhaps within the next 1,000 to 3,000 years, if we follow the patterns of previous interglacials. But there's a complication. Humans have added enormous amounts of carbon dioxide to the atmosphere. Since the Industrial Revolution began around 1775, atmospheric CO2 has increased from about 280 parts per million to over 400 parts per million, higher than at any time in at least the past 800,000 years, and likely the past 3 million years. This CO2 will remain in the atmosphere for thousands of years. While natural processes will gradually remove it, oceans will absorb some, weathering of rocks will consume some, plants will use some. These processes are slow. Even if humans stopped all emissions today, CO2 levels would remain elevated for millennia. High CO2 levels will keep global temperatures warm. Even if orbital conditions favor glaciation, the elevated temperatures may prevent snow from accumulating enough to form new ice sheets. Computer models suggest that the current CO2 levels could delay the next glaciation by at least 50,000 years, possibly 100,000 years or more. In effect, human activities have pushed Earth's climate out of the natural glacial-interglacial cycle that has characterized the past 2.5 million years. We are preventing the ice from returning, at least for the foreseeable future. This represents a fundamental change in how Earth's climate system operates. This raises profound questions about our responsibilities and our future. Are we preventing a natural climate change that would have been catastrophic for human civilization? Or are we creating an even more dangerous situation by warming the planet beyond conditions that human societies have ever experienced? If the Ice Age had continued its natural course, glaciers would eventually advance again, covering Canada, Scandinavia, and parts of northern Asia and the United States under ice thousands of feet thick. Sea levels would drop, exposing continental shelves. Climates worldwide would shift. The changes would be slow by human timescales, taking thousands of years, but they would be dramatic. Such changes would be difficult for human civilization to adapt to. Cities in northern regions would become uninhabitable. Agricultural regions would shift toward the equator. The infrastructure of modern society, built for current climate patterns, would need to be completely rebuilt. The social and economic disruptions would be enormous. From this perspective, preventing the next ice age might seem beneficial. If human greenhouse gas emissions delay or prevent glaciation, they spare future generations from having to deal with advancing ice sheets and all their consequences. But the warming we're causing creates its own problems. Current warming is happening much faster than any climate change during the Ice Age, except for the most abrupt events. Ecosystems and species that could adapt to gradual change over thousands of years struggle to cope with changes over decades. Sea levels are rising as current ice sheets in Greenland and Antarctica melt, threatening coastal communities where billions of people live. The rapid warming is also pushing climates toward conditions not seen in millions of years. Earth has been warmer in the deep past, but those warm periods occurred when the continents were in different positions, and species that exist today had not yet evolved. We don't know how current ecosystems will respond to such conditions. Moreover, the human systems that have developed over the past several thousand years, including agriculture, water resources, and settlement patterns, are all adapted to Holocene climate conditions. Rapid change disrupts these systems. Droughts, floods, heat waves, and other extreme weather events become more frequent and severe, causing human suffering and economic damage. So, while human activities may be preventing the next ice age, this is not necessarily a positive development. We are trading one set of climate problems, slow cooling and ice sheet advance, for a different set, rapid warming and ice sheet retreat. Both involve significant risks and challenges. The irony is that we are changing the climate on timescales relevant to ice ages, thousands to tens of thousands of years. But we're doing it fast, over a couple of centuries. This combination of speed and magnitude is unprecedented in recent Earth history. The ice core records show nothing like it over the past 800,000 years. Some scientists have proposed that if humans were to stop emissions and somehow remove much of the CO2 we've added to the atmosphere, natural orbital cycles might allow glaciation to resume, though on a delayed schedule. But removing CO2 on the massive scale needed would require technologies that don't yet exist and would be enormously expensive. Others argue that we should accept that we've fundamentally altered Earth's climate trajectory and focus on adapting to the warmer world we're creating rather than trying to restore past conditions. This would mean accepting that the Ice Age cycles are over, at least for the duration of elevated CO2 levels. The debate reflects deeper questions about humanity's relationship with Earth's systems. For most of human history, we adapted to climate changes we couldn't control. Now we've gained the power to influence climate on a global scale, but we're doing so unintentionally and without full understanding of the consequences. The Ice Age and its ending provide crucial lessons for thinking about these issues. They show that Earth's climate can change dramatically. They reveal that seemingly stable conditions, like our current warm interglacial, are actually temporary in the long term. They demonstrate that life can adapt to major changes, but that extinctions are also common when change is rapid or when species have nowhere to migrate. Perhaps most importantly, Ice Age research shows the power of feedback mechanisms in the climate system. Small changes can trigger much larger changes through positive feedbacks. Thresholds exist beyond which the climate system can shift rapidly into new states. Once certain changes occur, they can be difficult or impossible to reverse. These lessons are directly relevant to current climate change. We're conducting an uncontrolled experiment with Earth's climate system, pushing it in directions it hasn't gone in millions of years. The Ice Age record warns us that the climate system can surprise us, that changes can happen faster than models predict, and that the consequences can be severe. At the same time, Ice Age research also provides some reassurance. Life has survived dramatic climate changes before. Humans specifically have survived and thrived through major environmental changes. We are an adaptable species, capable of innovation and problem solving. Our ancestors made it through the Ice Age with Stone Age technology. Surely we can adapt to climate changes with all our modern knowledge and capabilities. The question is not whether humans will survive climate change, but how much suffering will occur, how many species will go extinct, how much of natural world will be lost, and what kind of world we will leave for future generations. These are ethical and practical questions that Ice Age science can inform, but not answer. What Ice Age research makes clear is that the stable climate of the past 10,000 years, which allowed human civilization to flourish, is not guaranteed. It could be disrupted by orbital cycles returning us to glacial conditions, or by human activities warming the planet. Either way, the era of stable climate may be ending. How we respond to this reality will define the 21st century and beyond. Do we aggressively reduce greenhouse gas emissions to limit warming? Do we develop technologies to remove CO2 from the atmosphere? Do we focus on adapting to whatever changes come? Do we accept that we've fundamentally altered Earth's climate trajectory and embrace our role as planetary managers? These questions don't have easy answers, but understanding Earth's Ice Age past provides essential context for thinking about climate present and future. The ice may be gone from most of the northern hemisphere, but the legacy of the Ice Age remains in our landscapes, our ecosystems, our species, and now in the choices we face about our climatic future. Lessons from a frozen world. As our journey through the Ice Age draws to a close, you lie here now, warm and comfortable, in a world that looks nothing like the frozen landscapes we've explored tonight. Outside your window, the world is not covered in glaciers thousands of feet thick. You do not need to hunt mammoth for survival. You do not live in a cave or a shelter made from mammoth bones. The Ice Age is over, at least for now. Yet the world around you is fundamentally shaped by that ancient cold. The valley where you live might have been carved by glaciers. The soil in your garden might have been deposited by ice sheets or their meltwater. The lakes you visit on summer days might fill basins scoured by ice. The species of trees, birds, and other wildlife you see every day are descended from populations that survived the Ice Age, their distributions and genetic diversity still reflecting those ancient refugia. More profoundly, you yourself are shaped by the Ice Age. Your species emerged during that time, adapted to its challenges, spread across the world, navigating its changing climates. The cognitive abilities that make you human, your capacity for planning, cooperation, innovation, and symbolic thought, were honed by Ice Age pressures. The stable climate that has existed for the past 11,000 years, which made civilization possible, is itself a product of the Ice Age's ending. Throughout this long night's journey, we have discovered that Earth during the Ice Age was not a dead, frozen wasteland, but a dynamic, complex world. Yes, it was cold. Ice covered vast areas. Sea levels were hundreds of feet lower, but life thrived. Ecosystems were productive. Animals as magnificent as any alive today. Mammoths, cave lions, dire wolves roamed landscapes as diverse as modern ones. Humans not only survived in this world, but flourished, developing sophisticated tools, creating stunning art, building complex societies. Our ancestors were not crude cavemen barely clinging to survival, but intelligent, adaptable people who mastered their environment and laid the foundations for everything that came after. We have learned that climate change is not something new, but a fundamental characteristic of Earth's system. The planet has undergone dramatic changes repeatedly throughout its history. Ice ages have come and gone, sea levels have risen and fallen, species have adapted, migrated, or gone extinct. Change is the norm, not stability. But we have also learned that the pace of change matters. Gradual changes over thousands of years allow species to adapt and migrate. Rapid changes over decades or centuries can overwhelm adaptive capacity, leading to extinctions and ecosystem collapses. The Ice Age climate changed dramatically, but usually slowly enough for life to keep pace. The rapid climate change humans are now causing is different. We are pushing temperatures higher, faster than any natural change in recent Earth history. We are doing so at a time when human land use has fragmented habitats, making it difficult for species to migrate to more suitable areas. The combination creates unprecedented risks. Yet, Ice Age research also provides hope. It shows that life is resilient. It shows that humans are adaptable. It shows that major changes can lead to new opportunities as well as challenges. When the Ice Age ended, sea levels rose and flooded coastal areas, but they also created new habitats. Forests spread across formerly glaciated lands, increasing biodiversity. The stable climate enabled agriculture and civilization. Similarly, while current climate change poses serious challenges, it also presents opportunities. The changes force us to rethink how we produce energy, how we use resources, how we design our cities and infrastructure. Meeting these challenges could lead to innovations that improve human life in multiple ways. The Ice Age teaches us humility. For all our technology and knowledge, we are still subject to Earth's systems, still dependent on climate, still vulnerable to environmental changes. The great civilizations of the past could not prevent the ice from advancing or retreating. Neither can we. Ultimately, though, we can influence the timing and magnitude of changes. But the Ice Age also teaches us confidence. Our ancestors survived and thrived in conditions far harsher than any we face. They crossed frozen steppes, hunted megafauna, and created beautiful art with only stone tools and fire. They were tough, smart, and resourceful. We inherit those qualities. Whatever challenges climate change brings, humans will adapt and endure. As you drift towards sleep, let your mind rest with these thoughts. Earth has been through dramatic changes before, and will again. Life adapts, the planet endures, the ice came and went, came again and went again, in cycles spanning hundreds of thousands of years. Each time, life found ways to survive and even thrive. The stable climate you've known, that your parents and grandparents and ancestors for hundreds of generations have known, is in one sense an anomaly, a brief warm period between ice ages. In another sense, it's the only climate human civilization has ever known. The conditions that allowed everything from agriculture to cities to modern technology to develop. Whether that stability continues, whether the ice returns in the distant future, or we prevent it through our emissions. Whether we adapt successfully to the changes we're causing, these are questions for future generations to answer. Tonight, you can rest in the knowledge that you understand something of Earth's past, the frozen world that shaped the planet you inhabit, the lessons that history provides. If you found this journey through the Ice Age enlightening, if these explorations of Earth's frozen past brought you new understanding and wonder, please like this video and subscribe to the channel. I create content like this several times each week, exploring Earth's history, the forces that have shaped our planet, the creatures that have walked its surface, all designed to inform your mind while helping your body relax toward restful sleep. Share your thoughts in the comments. Did you know Earth's climate had changed so dramatically? Does understanding the Ice Age change how you think about current climate change? What other periods of Earth's history would you like to explore? Thank you for traveling with me tonight across 20,000 years, from the height of the last glaciation to the present day. Thank you for your curiosity, your attention, your willingness to explore deep time, and to see the world from perspectives that stretch beyond human lifetimes. The ice sheets that covered continents have melted. The mammoths and cave lions are extinct. The Ice Age humans who hunted and created art are long gone, their lives preserved only in bones and artifacts. But the world they inhabited, the challenges they faced, the adaptations they made, all echo forward to the present, shaping the earth you live on, and even shaping you. Rest now, knowing you understand a little more about where you came from, about the dynamic planet that is your home, about the long history that led to this moment. Rest knowing that Earth has been through dramatic changes before, and will again, that life persists, that humans adapt, that even in the coldest times, warmth can be found. The Ice Age is over, but its legacy surrounds you. Sleep peacefully in the warm world that emerged when the ice retreated, carrying with you the knowledge of that frozen time that shaped everything you know. Good night, and may your dreams be filled with wonder at Earth's remarkable history and hope for its future.